So I just want to welcome again everybody to tonight's National Weather Service Boston webinar on the tropical tornadoes. I'm Joe Deli Carpini, the Science and Operations Officer, and with me is Rodney Chai, one of our meteorologists, and lately our severe weather hound. You'll see him in more winter weather as we turn the calendar into December, January, February. But Rodney was a great help in putting his presentation together tonight. So we're going to kind of tag team on this presentation, and we'll also have our usual weather briefing at the end. So just to start with an overview of what we're going to present tonight, there were, if you remember, several weak tornadoes. They were all EF0, affected our region in late August and early September. They were all from the remnants of tropical cyclones. On August 19th, we had two tornadoes from the remnants of Fred. That was a storm that struck the Gulf Coast initially. On the 23rd, we had three tornadoes from Tropical Storm Henri, which made landfall near Westerly. That was on a Sunday morning. And then on September 2nd, one tornado on Cape Cod from the remnants of Ida. So we're going to go through a little bit from each of those storms. But you'll notice a lot of commonalities between all three of those setups. They all formed in what we call kind of classic environments for decaying tropical cyclones. Whenever we have a remnant moving over us, even though it's kind of weakened and really no longer has its name or any structure to it, still usually produces a lot of tropical moisture, streams up into the area. They also have a lot of low-level shear, so we're going to be using some technical terms. We'll try and explain them as we go along, but for those who aren't familiar, when we talk about shear, we're talking about the change of direction, wind direction with height. Or sometimes wind speed with height. But in this case, it's more wind direction. So you might have a southeast wind at ground, at the ground level. And then as you go up a few thousand feet, the wind turns more out of the southwest and eventually the west. And it's that turning that kind of helps the storm gain its rotation. But you also need some instability right at the low levels. It's not a big day where it's hot and humid and we have a lot of instability like our typical summertime thunderstorms. Usually the instability is focused right in the lowest levels, maybe the lowest 5,000 feet or so. And we'll show some of that here on these maps tonight. Now for us, these are probably the hardest tornadoes to actually warn on with any lead time. The radar signatures, as you'll see, are very subtle, especially for the ones with Henri. So what I really tell our staff is we have to be aware a day or two ahead of time of what the environment's going to kind of look like, and anticipation is really key. So if we know we've got a tropical remnant coming in, we know we have the moisture, we know we have a little bit of instability, and we know we're going to have the wind shear, then we kind of have to actually pay a little closer attention to the signatures that are on the radar. Even a weak signature can be indicative of a tornado. So again, probably the most difficult to warn on. The lead time is usually very short, but we'll show you some examples of that tonight. So to get us started, I'm going to hand it off to Rodney, who's going to go through the first case, which was from the remnants of Fred. This was on August 19th, and we had two EF0 tornadoes. So Rodney, you can get us started.
Well, thank you so much, Joe. As Joe mentioned, these tornadoes are very hard to to identify on radar because, in such a tropical environment, there are numerous instances where you're going to have what looks like velocity couplets. And, if you kind of have to be careful as a warning, someone on the warning desk looking at radar, you cannot afford to warn on everything. Otherwise, you're going to get a lot of false alarms. And that's why it's really important to be able to know what are the really important things to look out for, and and really it's through experience like that. And so for this event, actually, we ended up having two tornadoes. The first of which actually crossed the state line from northeast Connecticut into central Massachusetts, and then the second one was, further north, across north central Mass, north of Worcester. So that was, and those two tornadoes were both EF0, so the lowest on the rating scale. Nonetheless, if you live in those communities, you did, suffer some damage, and those were associated with the remnants of Tropical Storm Fred. And this is the first tornado that again crossed the state line from Connecticut into Massachusetts, and it lasted about 10 minutes on the ground. Granted, the storm survey team, I mean, it was a very difficult job. I mean, it was a lot of difficult terrain and a lot of wooded areas. And in addition to that, at that time we were ramping up for what became Tropical Storm Henri. At that time there was still the real possibility of it being the first landfalling hurricane since Bob in 1991. So you can imagine it was we have to juggle a lot of things. We have to do storm survey and also have to prepare for Henri. And so this one, it was lasted about 5 miles. It was discontinuous. It actually ended as a water spout in Webster Lake, and thankfully no injuries or deaths. And this was actually a video of the water spout crossing Webster Lake. I'm not going to try to pronounce the name of the lake, and you can see, very good footage of the water spout. And we ended up concluding that it was from the same tornado that started in Connecticut. And this was where the tornado started. And our storm survey team took so these pictures were from both social media, our Sky One spotters, and the storm survey team. And you can see quite a bit of damage. I mean, it was a high-end EF0. It could have been EF1. A lot of power lines down and the trees down as well. And this pictures from the leader of the storm survey team, Bill Leatham, and he, you can see the tree snapped in half, and this is actually the damage from someone's backyard. And the second tornado of the day, so this one was a much shorter tornado. It happened in Clinton, Massachusetts. It lasted only a minute, but it was on the ground, and again caused quite a bit of damage. Thankfully, no injuries. And again, this is a picture from Bill. You can see quite a bit of tree damage there, and a rather big tree uprooted. And you can see the power lines down, and someone's roof got damaged. And there's more damage photos from Clinton, Massachusetts. And some of you may ask, how do we determine the rating of the tornadoes? So without going into too much detail, so we do have like a checklist that we go through, and based on the ground evidence, what was damaged, the extent of the damage, what were damaged, there's kind of like an estimate maximum wind speed, and based on the evidence, the maximum wind speed was determined to be 80 miles per hour, which put it as a high-end EF0 tornado. And so let's take a look at the environment. So as forecasters, it's always important for us to recognize the environment that we have, and when you come on shift, you kind of ask yourself, what are the hazards that I'm going to focus on today? And so taking a look at this is actually all the way up nearly 40,000 feet. So that's basically at the top of the atmosphere that we are interested in. And notice that the yellow shaded area, that's basically what we call a jet max, and estimated to be around 60 knots. And that's kind of west of New England. And that kind of puts us in, approximately in the right entrance region of the jet streak. And so if you look towards the bottom right of the image, there's actually a graphic that shows you how we diagnose a jet streak. And notice where it says DIV, that's divergence at the upper levels. So, we talk a lot about low-level convergence. and the upward rising motion of air, and eventually the air would hit a ceiling in the atmosphere and it would diverge. So that's the opposite of convergence. So if you have air that is being diverging at the top of the atmospheric column, you're going to help encourage low level convergence, and that's what we look for when we look at the upper level jet stream diagram. We want to see evidence of divergence, and in this case, by being at the right entrance region, there's upper level divergence, and it encourages large scale lifting. And here's taking a look at about 18,000 feet above sea level, and notice how we have a southwesterly flow. And when we have southwesterly flow, that maintains the flow of tropical moisture, and because you can kind of trace the moisture all the way into the Gulf of Mexico. And in addition, notice there's kind of like a dip in the lines, and that's actually indicative of a weak trough, and the trough further acts as a further source of lift. And going further down to about 2,500 feet above sea level, notice there's a closed low, and where Joe has his cursor right now, you can see that the closing off of the contour lines and west of New England. And the result of this is that you have convergent flow across the region, which again further helps enhance low level lift. Taking a look at the surface analysis, we kind of drew out, notice the red line, that's the approximate location of the warm front. And I like to tell people that in severe weather, never trust a warm front, because whenever you have a warm front, it can act as a focal point for low-level spin-ups. That may be sufficient to result in tornadoes. And further analyzing the environment for the first 3 kilometers. So what you're looking at in the upper panels, that's the 0 to 3 kilometers CAPE, or instability, as well as vorticity. So this is not like a supercell environment, where you have overshooting tops, going to 30,000 feet, 50,000 feet. This is a low level environment for weak tornadoes. So we want to focus on the instability and amount of spin in the first 3 kilometers. So you can see that there's about 50 to 100 units of 0 to 3 kilometer CAPE, and that's highlighted in the red lines, and the vorticity is highlighted in the blue line. So if you have instability and you have spin in the atmosphere, those are usually the prerequisites for possible spin-ups. And the bottom panels, you can see that's the 0 to 1 kilometer storm relative helicity. And notice that they are roughly where you see the darker blue lines, that's about 100 units of SRH. And so because we have instability, because we have spin in the atmosphere, you add 50 to 100 units of storm relative helicity, you can really get something going. And notice that if you combine all the parameters, that's basically eastern Connecticut into northeast Massachusetts. And and these are the products that you're looking at here. These are the derived products. So based on what we the instability, the shear, and the low level helicity, you put all this into a formula, and then you can compute the probability of EF0 plus and EF2 plus tornadoes. And notice that you have about 15% probability of EF0 tornadoes, and the probability of EF2 tornadoes is actually non-zero as well. It's about 1%, but it's very unlikely. So it's more likely you're going to get weak tornadoes, which was what we saw. And the other thing is sometimes we look at the SIG-TOR parameter or the significant tornado parameter. You have to kind of take this with a grain of salt, and but these are further resources that we can look at to kind of confirm our suspicion or hypothesis. And this is the SPC Storm Prediction Center. They highlighted a 2% probability of tornadoes across northeast Connecticut into eastern Mass. And the SPC did issue a mesoscale discussion. They do that every now and then when they have when there are significant features that they want to highlight to the public. And you can see where they hatched the purple hatched area. That's where they believe there could be some weak rotating storms. And notice how you actually have a stored boundary where you have the blue and red icons on opposite sides. That's a stored boundary, and that became a further focus for storms. And this is just a radar loop of what happened, and this was for the first tornado. So you kind of focus on the velocity product in the top right corner, and notice you can see the couplet basically tracking from northeast Connecticut into to Webster, Massachusetts. And and because these are weak tornadoes, you're not going to see like great indication on the correlation coefficient product, which is the bottom right corner. But you can still kind of see a little bit of the debris signature, but it's not like tremendous. So in this case, the telltale sign is you want to see a very tight rotational couplet on the velocity product. And this was for the second tornado, a very short lived, only 1 minute on the ground. But besides the velocity product in the top right corner, you can see the couplet. The bottom right corner, you can see what is called the N-rod product, the normalized rotation product. And if you overlap the rotational couplet in the velocity product with the N-rod product, it increases the confidence for to issue a tornado warning. And finally, if you look at the velocity product, you take the inbound, which is the green color, and the outbound wind, which is the red color. You take the mean of the velocity, you get 22 knots of rotational velocity. In a typical severe weather environment, this is something you probably not want on, but because you want to see rotational velocity values much higher than that. But given that it is, the environment is full of spin, is full of helicity due to the remnants of the tropical storm, this is a kind of situation where you will actually lower your your standards for rotational velocity and warn on it, because basically in this case it has that look to it. It's very tightly coupled, and in addition there's actually the normalized rotation, the bottom right corner. So if you kind of combine the two together, it gives you confidence to go for tornado warning. And granted, there were limitations in this part of the of southern New England. The beam is at 2,800 feet and nearly perpendicular to the storm. So, but despite the constraints, I think the warning team did a great job, and we were able to get people to a safe place before the tornado struck. And so at this point, I'll hand it to Joe. He's going to talk about more tornadoes on a different day.
Okay, thanks, Rodney. So on to round two. This was associated with the remnants of Henri. This was on the 23rd. So, and these occurred late in the morning. So the first one was in Marlborough. and occurred around 11:40. This was an EF0 with winds of 65 miles an hour. Note a pretty short path length, 3/4 of a mile, and only a 10-yard width. No injuries or deaths, but did go through a populated section of Marlborough, including Route 9. So fortunately, there were no injuries or fatalities with this. The second one was a small one up in Bolton, Mass, a little farther north. This was at 12:30. It was similar strength at 60 to 65 miles an hour, which places it at an EF0. Small path length, 1/10 of a mile, 50-yard width, and again, no injuries reported or fatalities. And then the third one was a little bit later, early afternoon. This was in Stowe, small section there. Winds of about 65 to 70 miles per hour, which was an EF0. And again, about a 1/10 of a mile path length and 50-yard width, and no injuries or fatalities. So all small tornadoes, but did a little bit of damage as far as pretty much 2 trees, which we'll get into a little bit here. So let's take a look at the setup for this. And you'll see a lot of similarities to what Rodney actually showed. So this was in the morning prior to the tornadoes. These upper air maps are typically created at about 8 a.m. and 8 p.m. when we're in daylight time. Then we go to standard time there for 7 a.m. and 7 p.m. But looking at the jet stream level, again, close to about 40,000 feet, you notice there's that jet streak as Rodney showed in the other, but it's kind of right on top of us. And what that does, we don't necessarily get the good dynamics because the lift is kind of out here over the ocean or also up here over northern New England, but it definitely gives you a little bit of energy in the upper atmosphere. So anytime you see one of these jet streaks kind of over us or near us, you have to be a little concerned that there's a little bit of extra energy available in the atmosphere. And as we go down, you see this a little more notably at the 500 millibar, about 18,000 foot level. We've got that closed low associated with the remnants of Henri. And if you've seen our tornado reviews before, you'll know the closed low is one of our most common setups for severe weather and tornadoes. This is a little bit different. It's a tropical remnant, but still, what happens is we get a flow, first of all, of moisture, like Rodney talked about it as well. It has a lot of moisture with it. So even though we're not seeing a big stream of moisture, and you can follow these barbs to kind of get the wind direction. So this is actually out of the northeast. But so we're not seeing a big flow out of the Gulf. But this, don't forget, made landfall over us. It's still got a lot of moisture kind of within its circulation. So it's not like it's drying out or anything. And we still have a lot of southeast flow. If you kind of imagine a counterclockwise circulation, over southern New England, the winds are coming right out of the southeast, so we're getting a lot of this moisture coming in, and also some convergence at this level as well. And then if we go down a little bit lower, this is about 2,500 feet. Again, you see that closed low associated with the remnants of Henri, and a similar pattern of flow coming off the Atlantic. We've got a lot of moisture, as you can see here in the green contours, and also some convergence. You've got 25, 30 mile an hour winds out of the south running up into winds at about 10 miles per hour out of the southeast. So imagine, if you're in a car going 30 and there's a car in front of you going 10, you're going to catch up. And in this case, you don't have a crash. The air converges, it goes up. So you get a source of lift in this area too. So looking at the surface analysis, this is 11 a.m. and lo and behold, there's another warm front, like Rodney was mentioning. And this is, we have to have some sort of surface boundary in these situations to focus that low-level spin needed to produce the tornado, because these tornadoes don't form from aloft. They form right at the ground and spin up. It's almost a backwards process. So you need a boundary. Typically, it's a warm front, a stationary front. Sometimes it's even terrain that helps spin up the circulation. And in this case, you can see north of the warm front, it's pretty warm, and the temps are on the top, the dew points on the bottom. So you have upper 60s dew points, near 70. But to the south, you've got a really humid air mass. Dew points are well into the 70s, 74 at Nantucket. So you've got a tropical air mass coming over this boundary, and this is helping to set up that low-level spin that we always look for. So we'll go through a couple of the maps from the SPC mesoanalysis, similar to what Rodney showed, a few different ones. First, this is called effective bulk shear, and this is looking at the wind shear through about the lowest 6 kilometers, so a little bit deeper of a layer, but the effective shear means it's relative to essentially the storm's inflow or the storm depth. So it's kind of what can a thunderstorm, if it forms, how much shear can it really take advantage of? And you see here, got a good 35 knots here near the south coast. even into, a little bit later here by 2 p.m. into eastern Mass. So that's pretty good. 30, 35 knots is at least what you want. And then on the bottom panel, something we didn't talk about, but it's called lifting condensation level. And all that is you're lifting air to the point where it condenses. So a lower value is favorable. And why is that? Well, you want to that funnel to actually be able to come down to ground level to form the tornado. Of course, we don't root for that to happen, but the lower the LCL, the more likely it is that your cloud base can get close to that ground level. So these are in meters. And typically, if they're below 1,000 meters, that's pretty favorable. And here we're looking at about 500 meters. So definitely in the ballpark for that. Now let's go back to what Rodney showed, the 0 to 3 kilometer. Again, you're looking at roughly the lowest 6,000 feet. Looking at our CAPE, which is our instability in red, and our vorticity, which is the blue. Remember, that's just spin. It's just a fancy name for spin. So we're looking for areas where the two overlap. You want to see the red overlaid on top of the blue. Now, doesn't mean you're going to have a tornado. It's conditional, meaning you have to have a thunderstorm in that area. And again, it's not a lock, but it tells you that conditions are certainly more favorable if the storm is in this area that's overlapping than if it's outside of it. So by 10 a.m., we see this area off Long Island. You've got a little bit of CAPE in here, still in some instability over here in southern New England, but we're lacking that low-level spin. By 12 o'clock, you can see it's kind of getting into the area, and by now we've already had one tornado working on it. It's actually the second. But you might say, well, we've got the low level. I see a little max there of CAPE, but I don't see any blue. Well, sometimes gradients are important too. And you can see there's actually, it's hard to see, but the blue lines are just getting into the area here of Massachusetts near the Mass Pike. So often you can have these things form on gradients. It doesn't have to be the absolute value. And you can see that's kind of the same case by 2 p.m. You've got the maximum here approaching the New Hampshire border, but back here there's a good gradient of CAPE combined with some of that vorticity. So that's really an area we have to watch as well, not just for a complete overlap, but also the gradient or edges of where these overlap. Those are important too. A couple of other things to look at here at the top. This is called the surface mixing ratio. Just think of it as moisture. So we're looking for areas of kind of where there's a ridge of moisture. And you can certainly see that here on the right panel by 2 p.m. You've got one here. You've got one off the coast. So there's moisture coming into the area at low levels. Again, that's favorable to help induce that kind of surface spin. And our 0 to 1 kilometer helicity, remember, that's just essentially a measure of the shear. It's kind of low, but it's there. Normally, we look for values around 100, and we're just kind of shy of that. But again, we're just on the edge of some of those areas of 100. So it's kind of close enough. And again, these are model analyses, and they're kind of can be a little bit coarse. So they show a general pattern, but what's happening right down at the storm scale, so think down almost to the street level, can be a lot higher than what we're seeing on these maps. So we kind of take that with a grain of salt as well. So here's the outlook for that day. And again, a low probability because this is not a widespread event, but there was a 2% chance of tornadoes, and that means a point probability. So these are typically going to be low. Once you get up around 10, 15%, that's actually very high. So a low threat that correlates to a marginal risk for that day. And overall, I think that forecast worked out pretty well. 3 short-lived, very weak tornadoes across that area. Now let's take a look at the radar loop from these storms, and you'll notice from the remnants of Henri, you can see that you can kind of figure the low is to our west. You've got this large area of showers lifting north, and then you see these little kind of what we call discrete or separate storms here lifting north that have formed in this warm and humid air near the warm front. And those were actually the tornadoes. From a radar sampling standpoint, pretty good. We're in an area where the beam is roughly at the lowest level, about maybe 3,000 feet. And if I draw a line from the radar, you can see the storms are moving along what we call the radial. So the storms are moving away from the radar, but they're pretty much parallel. So we're getting some good sampling. And of course, my phone's ringing, but that's okay. All right, so let's zoom in a little bit here. And you can see for the first tornado at 11:39, not a big signal on here at all. What we're looking at in this couplet is 14 knots inbound in the green, 15 knots outbound. So our rotational velocity is the average of that, 14.5 knots. And really, that wouldn't raise many eyebrows at all. Typically, we want at least 25 knots, if not 30. In a typical storm, you look at the reflectivity, I don't see anything really like a hook or appendage or anything. nothing showing up in the CC at that couplet, and nothing in the normalized rotation. So pretty, pretty weak signal there. But at this point, the tornado was observed. We had reports of a funnel cloud, and at this point, it was touching down to the ground. So this was, the warning got out a little bit later, a couple of minutes once we had the report. But at this point, the tornado has lifted. You can see a little bit of weak normalized rotation, but very weak. You've got the couplet kind of falling apart. It's happening here is the storms are becoming outflow dominant. So you're seeing, not a lot of green, but a lot of red. So the outflow from the storm is taking over, and that means the circulation that produced the tornado is disrupted. So at this point, it's kind of falling apart, and that's kind of the end of the first tornado. Now, the next one is forming here at 1223. This was the one near Stowe. And you can see, you've got a broad rotation here. Again, not a very strong signal, 13, 14 knots, and nothing really in the reflectivity or the normalized rotation. But, something's happening here. You can see something's getting its act together. And just before the tornado, kudos to the day crew. They were on it. And, you're seeing a weak signature, but knowing the environment, knowing what happened with the earlier tornado in Marlborough, there's enough of a couplet here that they felt it was worth warning on. So they did, but you can see already this storm is becoming outflow dominant. It didn't last very long, but this is just before the tornado. And then at 109, I'm sorry, this is the Stowe tornado here. Again, broad, weak velocity couplet. Not much, nothing that would really raise any eyebrows to say it was a tornado, but this was just before in that case. So a tough situation to say at the very least. But they did a very good job and warned on 2 out of the 3. So with that now, I'm going to pass it back to Rodney, who's going to talk about our lone tornado on Cape Cod from Ida.
Okay, thank you, Joe. And this is the third tropical storm that produced tornadoes for us here in southern New England. And this tornado was located in Dennis, Massachusetts on the Cape. And so it actually was a nocturnal tornado. And so, it's, some of you who live on the Cape probably woken up by the tornado warning and had to go to the basement. And so basically it was EF0 tornado with a max wind speed of 75 miles per hour, path length of 0.1 miles. Thankfully, no injuries or fatalities. And we did receive feedback that at least one resident received a tornado warning, prior to 1 a.m. and was able to seek shelter in their basement. So that's actually a very good lead time of like 20, 30 minutes. And again, looking at the environment, very similar to what we have seen with Fred and Henri. And so this is looking at close to 40,000 feet again. In this case, the jet streak is actually quite a lot stronger than the previous 2 tropical remnants. So jet streak of almost 120 knots across southern Canada. That's almost like what you see in the fall, and as opposed to late summer. So this puts the right entrance region over southern New England. So again, with such a strong jet streak, you're going to have strong upper level divergence, and which provides a source for broad scale lifting. Going down to 18,000 feet, again, so you see where it's highlighted in yellow, that's, there's a broad upper level trough across the eastern US. And notice the winds are out of the southwest, which brings in the tropical moisture. And also note the narrow band of 50 knot wind. So again, it's highlighted in the yellow zone. So down to 5,000 feet, so there's a close low over the mid-Atlantic states. That's actually the remnants from Ida. And notice there's a strong wind convergence over southern New England. So notice how the winds along the south coast are from the south to southeast, whereas, north of Route 2, that's the winds are actually, in this case, they are from the north. Or southwest. So in either case, you're going to have directional convergence. It's basically the winds coming together. And it sounds like like a beaten record right now, but again, there's actually a warm front right over the Cape, and that's around 12 a.m., 1 a.m. And again, it doesn't matter if it is middle of the night. There's no daytime heating. In this case, the warm front helps to focus low-level spin up that is needed for the tornadoes. Taking a look at the various parameters. So top left corner, that's 0 to 3 kilometers Cape, and surface vorticity. Again, the Cape or instability is highlighted in red. The blue is vorticity, where where the kind of overlap, that's where you want to pay close attention to. And unsurprisingly, Cape Cod and the islands were under the gun that night for possible spin-ups. And top right corner, you can see the 0 to 1 kilometer storm relative helicity. So there's quite a bit of low-level spin. I mean, and any storms that get going, they can, they're capable of producing spin-ups. Bottom left corner, that's effective shear, 0 to 6 kilometer shear. So you can see, pretty high values. In this case, you're talking about 350 to 500 units of shear. That's and usually you don't get that unless you get a tropical environment. And putting it all together, instability, spin, and shear, unsurprisingly, the probability of EF0 plus tornadoes is pretty high, 15 to 25%. And here's an observed sounding from New York City. So OKX is New York City. And so notice how, there are a few things here that are noteworthy. Number one, that's where you see the green line, the red line. The green line is the dew point, red line is the temperature of the air parcel. And notice how they are kind of close to each other. And that's indicative of a tropical environment where the atmosphere is full, just absolutely loaded with water. And we would, we'll talk about this in another webinar. Unfortunately, that the Ida was associated with significant flash flooding in New York City and the Mid-Atlantic states. And you look at the sounding, this is basically a loaded gun. And but the other thing that I want to talk about, look at how the winds shift direction in the lower part of the atmosphere, where Joe has his cursor right now. So further up the atmosphere, the winds are from the south, but very close to the ground, the winds are actually from due east, or even a little bit of northeasterly direction. And so when you get this kind of if you visualize the atmosphere in a three-dimensional way, you can kind of make out the rotation of the atmosphere. And if you look at the top right corner of this image, notice that's what we call the hodograph. And if you attend our severe weather workshop, you would learn a little bit about what a hodograph is. But essentially, that a hodograph is a way of visualizing how the winds change direction and speed with height. So, kind of putting it all together, so you have a very very moist environment. You have instability, shear, and spin. You're capable of producing spin ups. And this was the SPC outlook that night. And notice how they have a much of Rhode Island into southeast Massachusetts that's under the slight severe risk category. That's 2 out of 5. And then on the right hand side, that's the probability of tornadoes. So the highest risk, 10%, was actually over New Jersey into southeast PA, where they actually had an EF3, not too far from Philadelphia. and notice how they have the 5% area all the way to Cape Cod and the islands. And this was from from that night, the various mesoscale discussions being issued. So initially the concern was over Long Island and New York City, and eventually as the warm front lifted north, that threat migrated into our area, and that's you can see 11:20 p.m. and 3:30 a.m. and sure enough, I mean, the tornado kind of formed right along the nose of the warm front. And this was the tornado watch, again, initially over Long Island and New York City, and then eventually into Rhode Island and Southeast Massachusetts. And this was just a radar loop that night. No, once again, this is not a supercell environment. You're not going to see like a Hooke echo or anything. So, you look at this, I mean, maybe you couldn't really make much of it, but wait till you see the velocity. So here, 12:30 a.m. and so we are the tornado watch has been issued, and the midnight crew was kind of getting really on high alert for possible spin-ups across the South Coast and Cape Cod and the islands. And this was actually one of the first tornado warnings that the midnight crew issued. So notice in this case, kind of focus on the top right panel, that's the velocity product. And notice how you have the red and the green kind of together. So in this case, the couplets, so even though they appear to show rotation, they are actually convergence near 3,500 feet. And remember, that's where the warm front was approximately located at that time. So you're going to have convergence just based on the warm front. And, and thankfully no damage was reported on the Wynyard, although they were under a tornado warning. And this was kind of like a situation whereby it's really a close call, and unfortunately you're not going to get every call correct. So 30 minutes later, just after 1 a.m., again, so another tornado warning for Barnstable County, and in this case, it includes Barnstable and West Yarmouth. And again, focus on the velocity product. So you can kind of see it, the couplet. So remember, the red is outbound and green is inbound, and the radar is actually located to the northwest. So there's about 34 knots rotational velocity. It's pretty decent for a tropical environment. And towards the bottom left panel, that's the correlation coefficient product. So notice where you see the green and the blue pixels. That's an indication of a lowering of correlation coefficient. If it is just rain, you're going to get a correlation coefficient of 1 or 100%. So when you get things other than raindrops in the atmosphere, be it hail, or a debris, you're going to get the ratio to be below 0.9, sometimes 0.8. So in this case, there's actually some indication of debris in the atmosphere. There were no damage reports received, so potentially it was a water spout, just off the coast. And at 1:15 a.m., and that was so that's actually the one that produced a tornado. And so notice the strong convergence south of Yarmouth Port. And you have 35 knot outbound and 35 knot inbound, and which makes for 35 knot rotational velocity. And notice in the bottom right panel, you actually have a pretty good NROD, or normalized rotation. So that's NROD values of 1 to 1.5, very decent. So when you are able to overlap NROD with velocity, you can be pretty confident that that was a tornado. So in summary, it felt like an endless summers of tropical storms and tornadoes, and we do empathize. And there were several weak, all EF0 tornadoes. Thankfully, no injuries or fatalities from the remnants of tropical storm Fred, Henri, and Ida. And so in all, we covered 6 tornadoes from 3 different events, and the environments that the tornadoes form, these are all very classic environments for decaying tropical cyclones, plenty of tropical moisture, and also strong low-level shear, and in the presence of low-level instability. And these tornadoes are pretty challenging for our warning meteorologists, and you kind of have to balance between, you don't want to be overzealous with issuing the warnings, because that will lead to a high false alarm ratio, but also at the same time you need to know when to pull the trigger. And I think overall, the team did a great job of providing enough lead time and really minimizing the false alarm ratio. So and knowledge of the near storm environment is pivotal to anticipating this tornado. So, and at this time, I'll pass it back to Joe.
Okay, thanks, Rodney. Appreciate you going through 2 of the 3, and got through all of them here. Let's go and what do you say we answer some questions? So if you have any questions, don't forget you can use the chat box, which is in your control panel. First one's a comment from Sebastian. He's found great promise in using spectrum width in detecting possible tropical tornado spin-ups before they occur, looking for values around greater than 15 knots or so. So Sebastian, that is spectrum width is actually one of what we call the base products from the radar. So there are 3. One of them is reflectivity, which is, where's the rain. The other is base velocity, which is obviously the velocity. And the third is spectrum width. So spectrum width is used to detect areas of turbulence. So it's not on its own a good detector of tornadoes, but it's something that adds confidence. So what we do is we use it once we identify kind of a couplet, like Rodney was showing on those couplets there. If you have a pretty strong couplet and you've got high values of spectrum width, that means you have a very turbulent flow in that area, and that's something that can probably, once in a while nudge you to go more toward a tornado than not in the warning process. So yeah, we do use that, and good catch. It's definitely something that works. So from John, do we track the instances of false positives or false negatives with respect to tornado warnings, and is there a number you target? Yeah, we do. We're actually required by Congress to keep track of everything. And we report that out at the end of every fiscal year, which is the end of September, which is coming up. So we track what's called the probability of detection. So that's the number of tornadoes that occurred and the number that we've successfully warned on. We also track what's called the false alarm ratio, which is the number of tornado warnings issued and the number that did not verify. So nationally, those numbers, the false alarms are high. The probability of detection is relatively low when we compare it to other things like severe thunderstorms, winter storms, flash floods. Rodney, I don't remember off the top of my head, so maybe you can Google it as I'm talking here. I think the goal for detection is around 70%, and the false alarm, I want to say, is close to 60 or 50 or 60%. Whereas in other programs, we look for, maybe a detection rate around 90% and a false alarm around 30. But knowing the limitations of kind of the science, despite everything like Doppler radar and other things, those numbers, I think, it's close to that. But we do track them, John. And what we do is we use that verification to kind of do our best to improve our program. And in fact, a lot of the research that we presented here tonight and on our Southern New England Tornadoes webinar was a result of having pretty poor verification over the past 10 to 15 years. So we've kind of come a long way. And we've had Rodney, I think we've had a pretty good year this year with our tornado warnings. Maybe as we head into the fall, we can actually present some more verification. I think, folks would be interested in see actually how do we do? What's our batting average for different events? So we'll take note on that, Rodney.
Yeah, Joe, we do actually. Just reading Glenn's email. Glenn is our warning coordination meteorologist.
Yeah, go ahead.
And So we have a POD of 81%, which is very high,
Is
and
that's for
false
severe, all severe, Rodney?
also severe actually,
Okay,
and
yeah.
then the false alarm ratio of 29%.
Okay, so
Um,
yeah, so that would include severe thunderstorms and tornadoes. What they do is a combined severe metric. And then they also separate out tornadoes. So I'm not sure where we are on that, Rodney. But I know we're having probably one of the better years we've had since 2018 when we had a lot of them. So the way it works is when we have a lot of events, we tend to do better than the years we don't have a lot. So think about it as like a baseball player. You don't have a really representative average with just a handful of at bats a year. It's the players who play most of the season that you really get a good sense. So, but yeah, that's at least some measure there, Rodney. And yeah, maybe we can do something on our verification just to kind of give folks a sense of how we do in different, different types of weather. So, but that's something we do for Congress, believe it or not. Also from John, do tropical storm associated tornadoes tend to have a faster ground speed than your typical thunderstorm tornado? Um, Depends. A lot of times with these, they're on the ground just for a minute or two, very short time period. It really just depends on the low level wind. Talking about that 5,000 foot, 2,500 foot level. When we have stronger winds, and those, a lot of times in the fall, when we have like an October tornado, you'll see the storms moving very quickly, maybe 50 miles per hour, as opposed to ones that occur maybe in July where they're moving 20, 30 miles per hour. But in these environments, they tend to move pretty quick. But it just really kind of depends on the setup at the time, John. So it can vary quite a bit. From Eric, let's see. I'll throw this one to Rodney. It's a good meteorology question. So when looking at the different charts for wind speed, altitude is shown measured in millibars with approximate altitudes. Why is the analysis based on pressure instead of altitude? You want to take that one, Rodney?
yeah, sure, Joe. That's a great question. And so the reason why we use pressure instead of altitude is because, so just think of like say folks living out in Colorado, so like Denver. So Denver is a mile above sea level, 50 to 80 feet, and so for folks in Denver versus folks living in southern New England, we live so close to the sea level, and if we don't have another unit of measurement, for altitude. So in this case, we use pressure as a proxy for altitude. Um, because if you say, like 2,000 feet, above you, it's kind of different. Um, are you talking about with respect to sea level, or are you talking with respect to where you are located? So in this case, the short answer is the pressure is used as it kind of like standardizes the how we communicate um, in terms of atmospheric height, regardless of where you live, and regardless of your altitude above sea level. So hope that makes sense.
Yeah, and I think something else you can say, Rodney, is the kind of the depth of the atmosphere varies with temperature. So um, the atmosphere is maybe we could say it's kind of thicker when temperatures are warm and thinner or lower when it's cold. So if you just had a standard height, it's going to be affected by temperature. Whereas if we're on constant pressure, there's really kind of no impact. So if we look at a constant pressure surface, we can relate features across the country much more easily. So hope that makes sense. A little complicated, but um, trying to keep it simple. Let's see. A comment from Sebastian. Would you mind going back to the tornado wind damage table so I can take a screenshot? Yeah, here we go. And actually, you can look at this on the SPC website. If you just search uh, damage degree indicators SPC, you'll probably get the whole reference guide. And again, I just want to caution everybody: this is not the final answer, to determining a tornado. It's if you go back to our webinar that we did on storm surveys a while back on YouTube. This is just one part of the process. So again, we're looking at radar data, we're looking at damage on the ground, and we're talking to eyewitnesses. So um, it's a little subjective. It doesn't mean if you have trees uprooted, you have this amount of damage. It depends on the health of the trees, how many are down, a number of other factors. But this will get you in the ballpark. So again, it's freely available. It's a government publication. Just do a search SPC damage degree indicators, and that should take you to the whole guide, which contains a lot of information. So there you go, Sebastian. And I'll leave that up there for just a couple of minutes. Let's see. Looks like we have another from Ethan, and that's a long one. Ethan always has long questions. Let's see. In terms of tornado warnings in tropical situations, when they've been, let's see, I'm trying to read the whole thing here. In terms of tornado warnings with respect to tropical systems, are most tornado warnings issued in marginal situations like the one mentioned in the webinar, issued when they've been observed, not based on radar? It depends. These are, again, weak, so you kind of have to get a feeling for what's the thresholds of the day. So in this case, that first tornado was observed and then warned on because it was so weak. Normally, we wouldn't expect that to really do anything. So the observations came in really helpful, having that report of the funnel cloud, and then from there they can correlate. Okay, I'm seeing about the same signal up towards Stowe, and they issued a warning on that, and it actually worked out pretty well. So yeah, it just kind of depends. It's situationally dependent there. And Sebastian, the Plymouth State Weather Center, you can just do a search on that too, and they have a wealth of information. It's the Plymouth. Rodney, do you know what that is offhand? Maybe you can just toss it in the chat. Plymouth State Weather Center.
Yeah, Joe, I can.
Okay, so Rodney will help me out there, Sebastian, and put that in for you. From John, are forecasters able to track the progress of warm fronts that focus the tropical tornadoes in real time? Yes. We get the hourly observations, so we can either use the analysis from SPC, or we can do a hand analysis. We get the plot of the stations every hour, or even every 30 minutes, and we can kind of keep an eye on where it's going, and then use our the high-res models to kind of figure out where it's going like in the next few hours. So we certainly can. And from Ethan asking about the EF0 plus probabilities. Let's see, the numbers for derived product, use the numbers that it does. Those are point probabilities. So again, it's about the chance of a tornado occurring within 25 miles of a given point. So they're going to be relatively low. 15% is actually a very high value. 25% is a very high value, even though they might seem low. The marginal, a marginal severe risk is 2%. A slight risk is when you're getting up toward 5, 10%. So when you're up at 15, that's pretty healthy. So again, the probability of occurrence within 25 miles of a point. And let's see, just going through a few. We got a few questions in here. Let's see. Max is asking about tomorrow. We'll get to that, Max. Hold on. Let's see. Question about a likelihood of a winter tornado near Boston. Rodney, you want to take that? What do you think? Fall, I think, absolutely. Winter? I don't know, maybe.
Yeah, I think that, Joe, and that's an interesting question. It's very unlikely just because while you could have very good jet dynamics, like jet streaks in excess of 120 knots, but in this case, it's just not enough instability. And when you get the ocean temperature are kind of in the 30s and 40s, so you get a northeast flow with our nor'easters, you're just going to get a very stable atmosphere in that respect. But you could get thunder snow though, under the right environment. So, but I just don't think the environment would be good enough for tornadoes. The only exception I would say is if you think about maybe like like last Christmas we get temperatures went up into the 60s briefly, and that was a very anomalous warm pattern. So you need the warmth, and you need the dew points at least into the 50s. Otherwise, you're not just going to cut it for anything other than thunder snow. So hopefully that makes sense.
Yeah, I was just going to say that Christmas last year was probably a good example of maybe we could get one because there was some instability. And this actually follows on a good question from Carrie. How is a setup for a tropical storm different from the setup in like Tornado Alley? And so the difference is it's all in the low levels. That's what we showed tonight. So in a typical spring severe weather setup, say we go back to the June 1st, 2011 tornadoes, that was a plains environment. So we had a lot of instability, very strong wind shear. I think the hot, very humid weather. Now, these we showed tonight, everything was focused down low in a small portion of the atmosphere. We always say 0 to 3 kilometers. So that's, 6,000 feet, roughly, maybe 7,000 feet. But so everything is focused down there. The instability is down low, the shear is down low, and you have a little boundary for spin up. So a little bit of a different environment in these tropical setups, but as opposed to the peak ones we see in the summertime, which are very rare around here, by the way. Most of our tornado events are similar to the ones we showed tonight. Everything is concentrated down low. So that's what we want to look for in our tornado setup. So let's see. From Drew, a comment here. When he was a kid in the 90s, early 2000s, never recalled this much tornado activity than the past few years. Is this due to technology advancements or weather becoming more severe? Rodney, I'd say it's probably both. We definitely have we know we have kind of a warming climate that gives us more energy, usually a stronger jet stream, so stronger wind shear. But we're also able to detect them much more easily. We get people on social media. We have radar. We have the 1-minute satellite. A lot more tools to detect it. So, I think maybe 15, 20 years ago, we might not have heard about that tornado in Dennis in the middle of the night. It might just have come across as some trees down. Or the ones even in Stowe or Marlborough if they weren't spotted. So I think it's a little bit of both. So Rodney, I don't know if you have a take on that.
Yeah, Joe, I absolutely agree with you. I think it's both. It's just because of the warming climate and also just really better detection technology, and also thanks to all of you. I mean, will give us so much information either through social media or you call in with your information. So I agree with Joe, and thank you very much.
Yeah, and let's see just a couple more, and then we'll get on to our weather briefing. I don't want to hold folks too long tonight. But if we don't get to your question, you can also feel free to email me, and Rodney and I will definitely get back to you. Let's see from Robert. I know that when a tropical storm or hurricane weakens, the size tends to get very big and less organized. Is the creation of the spin-ups the results of a tropical cyclone's angular momentum weakening, almost like energy is being flung out of the system? It just has to do more, I think, with the wind field within it. There's still a lot of, as we call it, the shear at low levels or change of wind direction. There's always some sort of remnant circulation, a little bit, think of it like a weak low that's present. It takes a long time to decay when it's purely tropical, which these were. So these weren't turning into like our nor'easters, like most of them do. These stayed tropical right over us, and the remnants. We have the moisture, we have the instability, and we have that turning wind direction. So that's kind of more of the reason. So let's see. From Andrew, just listening to Rodney, do late season tropical systems have less of a chance of producing tornadoes, i.e. October and later, because instability is less typically, but in some cases you can have the instability, and there's actually a little bit of a fall peak in tornadoes on the East Coast. We had them back in 2018 in October. So you still have to watch the tropical systems even in October. So something to keep an eye out. But again, it's that you have to have that low level instability to really be able to generate them. If you don't have it, you won't really see much of anything. Let's see. So from Elizabeth, and we'll finish up here and then go to our briefing. When did the NWS start looking to forecast tornadoes and remnants of tropical storms? I don't remember us forecasting these in my youth or even the 70s. And no, typically they would issue just for the kind of the landfalling tropical storm, the landfalling hurricane. And then there wasn't much really known about the remnants of these, but there's been a lot of research the past 10, 20 years. So we know the environment's a lot better. We're able to anticipate them. And for that last case that Rodney showed, you'll notice they issued quite a few mesoscale discussions and even issued the 2 watches. The watches were actually issued at the request of the New York office and our office. Rodney, I think it was it Bill Leatham who actually called them up and based on what was happening, kind of said, hey, heads up, we're kind of an environment here that's pretty favorable and out of the ordinary, and I think we really want to have a watch put up here. So, Rodney, I think that was the case, right, with the remnants of Ida?
Yeah, it was Bill, Joe. And also for context, the SPC is located in Oklahoma, so they're more used to dealing with like supercell environment, and in this case, and that's why collaboration is so important, because we share our expertise with each other, and in this case we got the tornado watch up upon collaboration with the Storm Prediction Center.
All right, so at this point, that's it for the questions we're going to answer now. We're going to move on to get to our briefing.